60s.
And then went off the what?
60s.
Oh, the 60s, no. It's the
Late
70s.
1960s.
He's aging himself. And then went off to the Naval Research Lab for a little bit, then to UCLA, and then came back to Cornell, luckily, and has been with us ever since. He leads a very important research group, the Lab of Plasma Studies on campus, that among other things have been looking at the sort of science questions related to inertial and magneto confinement nuclear fusion. And so he's going to tell us hopefully a little bit about that work today. David?
Thank you very much. I should admit right up front that we have 2 speakers on fusion this semester, so I was planning to leave most of that, in fact, virtually all of it, to those 2 speakers. The first one is next week. Bring all your friends who might be interested in fusion next week to hear about inertial confinement fusion and maybe a little on magneto-inertial fusion. And then on the 28th of February, the last seminar in February, we have Scott Shue, who is going to be telling us about magneto-inertial fusion in particular, but also magnetic confinement fusion. So with that much of a introduction to what's to come, let me tell you that there might be a few of you here who were here last year. I left out my slide to find, there it is. There it is. How many of you are here because of the course listing? How many of you are here because you took last semester's course? Okay. Email message. Very good. It worked. A friend told you? Okay. Well, please bring your friend back if the friend isn't here now. We have plenty of space. Any other way you found out? All right. How did you find out?
The website.
All of those things. Oh, the website.
The website.
The website. All right. And
Atkinson Center.
Atkinson Center. Okay. All right. So let me go back to the beginning. And the reason I said that is because the 3 of you who were here last semester may, but probably don't, recognize this slide. It's the only thing that's the same as my starting talk slide last time. The rest of them have all changed. The only thing changed here is the date and the title. It's a little bit different because the emphasis is going to be a little different today. In fact, quite a bit different. And so I think even the 3 of you who may have seen the previous version of this slide will see something considerably different today. There'll be a brief introduction to the energy seminar as a course first, and then we'll get into the meat of the seminar. The main thing to make sure you realize is that there are requirements for this class. It's not an ordinary energy seminar, an ordinary seminar. You actually get a grade. If you sign up for a grade, you can get SU or you can get a letter grade. But that means you have to do something, and the do something means you have to turn in some summaries. For SU, you need to turn in at least 9 summaries. There are 14 seminars. And for an A, you need to turn in 13 summaries. If you have a problem, there is a way to do a makeup, so don't worry if you do miss one for illness. If you know you're going to miss a bunch, I certainly suggest that you take it SU instead of letter grade because you need fewer summaries. And also, you may, if you know you're going to miss even more, you may want to audit instead. There's official information about what you have to do on the Blackboard website, and so I refer you to that rather than trying to tell you now. But the course information document is the one that has all of the actual requirements for the course, and summaries are supposed to be turned in to Clear. These slides will be posted, so all of this that you see here will be available to you. Okay, a few additional words. We do read these summaries. Please make them interesting. In addition, you will be invited to, in fact, you have to attend post-seminar lunches so that you meet the speakers and interact with them, and we ask you to sign up for that. The sign-up sheet is also on the website, and so please plan on attending 3. If you have a problem because you have a post-seminar course conflict, then there is a way of taking care of that that's in the course information sheet as well. It is very important for you to sign in each week. There is a sign-in sheet that's going around. It's someplace out there now. Wherever it is, let's send it around again because of the people who have come in just now. And the reason for that is because we post these slides. Every week, if we possibly can, we post slides. And we don't want people writing summaries without attending the seminars. And so we need to know that you came here if you are going to use the slides to write your talk. Okay, makeups are going to be announced. We do like to have people quiet and paying attention. For example, we have the CEO of New York State Gas and Electric coming here in April. That's a pretty high-level person. We all will be very embarrassed if there are people who are texting and browsing the web at the time when that man is in the room. And we would like to have you paying attention to him because he might actually say something that's important, as might I. So please pay attention and try to get here on time and turn off your cell phones. Okay, I think that's enough. So let's go back to the first 2 pictures again and talk about solar energy as one of the resources. You all know about the sun. A few things you may not know specifically. The 1 kilowatt per meter squared reaching the surface of the Earth is something you probably mostly know about because that's the basis of photovoltaic power, or even the solar thermal power is concentrating the energy from the sun into electricity via photovoltaic cells or solar thermal mirrors heating a fluid. What you may or may not know is that we only need to harvest about 0.01% of the sun's energy if we wanted to use only solar power for powering everything on Earth. It would be a little difficult on the dark side of the Earth without lots of batteries or energy storage, but nevertheless, we could do that. So solar power is a very good resource for us to be emphasizing. And now I'm not getting this one either. So it must be I may have turned it off by accident. No. Well, anyway, we can use this. And I expect that you also don't know that any one of you could calculate this piece of information at the bottom just by knowing what the man next week is going to tell you about the energy release in fusion reactions. The sun is providing all of that energy that reaches the Earth and goes out into the rest of the solar system, of course, by converting 800 million tons of hydrogen to helium per second. Fusion reactions. It's actually a chain of 4 reactions. And that's where the helium comes from that is in the moon, on the moon's surface. And so one of these days we may be powering spaceships using the helium-3, not the ordinary helium-4, but helium-3 that's on the moon. It's one of the interim steps, and sometimes it escapes. The helium-3 gets off in the solar wind and ends up in the moon, and we can harvest that for space transportation someday. perhaps. And I've already mentioned the 2 talks. 20 square kilometers per gigawatt in practice, assuming 20% efficient solar cells, a little bit higher efficiency for solar thermal, but there's a lot more hardware there before you end up with electricity. All right, so let's go the opposite direction for a minute. Talk about coal. 1 gigawatt electric takes 3 million tons of coal. So it's got to be mined. It's got to be transported from wherever it's mined to wherever the power plant is. And then it has to be burned. And the result of burning is about 10% of that 3 million tons ends up as ash. And there's also some NOx and, whoops, go back up there. There's nitrogen, nitrates, and nitric oxide, and there's sulfur dioxide, and those are not so good for people. But coming back here, I used to be, Lyndon didn't tell you that the energy seminar's been going since 1991. And during the first 20 of those 30 years, I used to be able to say, how many of you have been caught by the coal train going across the west end of Ithaca? And there were always a bunch of people out in the audience who could say, yeah, I've been caught by that coal train. 100 cars went by the west end of Ithaca, blocking traffic going up the West Hill every 3rd day. But that was because it was only a 350 megawatt power plant. So for this 1 gigawatt electric hypothetical power plant, such as one up by Rochester, it takes one 100-car coal train a day to provide the coal for that power plant. So it's not just a matter of mining and burning, it's a serious transportation issue and a serious effect on local situations. I've written there, coal resources on Earth are good for about, well, somewhat more than 300 years if we kept on burning it at the rate we and the Chinese are burning it. They would run out a little sooner in China than we would. I'm not quite sure what the situation is in India, but while the use is shrinking in much of the world, it is actually still growing in China and India, and so it is important for us somehow or other to get ourselves away from not only keeping the coal burning plants going, but having new ones continue to be built. In order to anticipate that happening, we have to have an alternative. So here is my collection of alternatives. We can't get rid of coal until we're ready to use one of these other power sources. Fission could do it, but there's a fair amount of opposition to fission. Natural gas effectively is taking over from coal in the United States, and gradually, at least in most places in the United States, is and will replace most coal. Hydro certainly won't in the United States. We've got about 10% of our electricity production from hydro, and we probably will not be able to go much further than 10% in the US. We use a lot of oil, but not for electricity generation. It's cars, and I will show you a pie chart of the total energy use in a while that will show in the United States we're using more oil than natural gas because of transportation. You probably know that we're going to try geothermal here at Cornell as a demonstration, or maybe not, that it works. And so this is on the way if it's feasible, but it's a long ways away. My favorite, of course, is fusion, but it's a little ways away too, and we'll leave it for the future speakers to tell you about that. Got some good things to say about wind locally. So, well, let me leave that for a later slide. But let's first look back and have a historical perspective of this. And in order to do that, I have taken some slides off the BP website and also off the Department of Energy's Energy Information Agency website. So if you like what you see in terms of having a graph that you would like to use for some presentation you're about to give, then this is a good website for kind of overall worldwide usage and area usage. And I assume that BP isn't fooling us. They have no particular reason to, since they're broad enough in their in what they sell that it doesn't really matter to them, I suspect. Okay. This is something that is on the present, in the most recent set of slides that they give. There's an introduction to the slides. And in that introduction, this is what it says. Growth in overall energy demand was stronger in 2017. This is the 2018 report, which comes out during 2018, so it goes through 2017. Gains in energy efficiency were down. We're buying too many SUVs. It probably isn't that. Coal consumption grew for the first time in 4 years. At the same time, there was strong growth in renewables and natural gas. So I'm going to show you that in a minute. Together, the renewables and natural gas accounted for 60% of the overall increase in total energy consumption. That means 40% went to coal, unfortunately. Carbon emissions increased, and in this weird unit of millions of tons of oil equivalent, these were the increases. For gas, 91, oil, 77. You know, that's not a lot different. That means there's a lot more oil use in addition to a lot more gas use. Renewables were third. Coal's down here at half the renewable increase, so that's a good thing. The increase in energy generation in energy need is being taken up by most things other than coal. Okay, so here is one of the first of those nice slides from BP. Primary energy use. So what you see down there at the bottom is oil is the biggest, and up there at the top, coal is a close second. Gas throughout the world is third, and then you see hiding there in these little slips here, that one is nuclear. Whoops, did it again. And that one is hydroelectricity, which is actually growing, as you'll see in a minute. And then renewables are at least perceptible now. I mean, look back here when we started the energy seminar, that was renewables barely visible. Everything here is put into the same energy unit, millions of tons of oil equivalent, so that we're judging the amount of natural gas being used by its energy content relative to oil. And as the renewable that is gaining the most in actual energy, the world use of hydroelectricity is increasing, and it looks like a big thing because the scale on the right has changed. So I'm going to go back to the other one. So you'll see that we're talking about 900 million tons of oil equivalent. Just 900 is good enough for the moment. And let's, whoops, I went forward instead of back. We're talking about 13,000 there in the total. So even though hydro is a substantial contribution here, the blue one, it's still a small piece of this action. And down here is North America. So the United States and Canada are pretty much saturated in the hydro contribution, as is Europe. I believe that's Europe. But you see in the Asia-Pacific region, hydro is growing just like everything else is growing. And then, wrong direction again.